In this video, I will show how to find active IR and Raman modes of CO ligands in a complex. So question is, consider ML₄ CO2 transmetal complex, determine the active infrared and Raman modes of the complex. So we have firstly steps. These are our solution steps. Firstly, we need to draw the complex. Then we should find the point group by using a symmetry tree, which is here. And we have to make a reducible representation for CO ligands. And then by using character table, we can determine the infrared and Raman modes of the CO. So firstly, I need a space to draw the molecule. So this is a transmetal complex, which means that one of the CO is on the top, and maybe I should draw the CO like this. We have a metal, and we have another CO, and we have 4 ligands. So we have to find the reducible representation for this molecule, and to do that we draw the complex, and I need to find the point group. So we have a symmetry tree here, and by using symmetry tree I can find the point group. So is system linear? The answer is no. This is not a linear system. We don't have multiple higher order axes, so the answer is definitely no here. This is not an octahedral geometry, since the ligands are different. Do we have a CN axis? The answer is yes. We have C4 axis here. So the answer is yes. Is there an orthogonal CN, C2 to C4? The answer is yes. We have one axis from here, which is orthogonal to the C4, and we have one more, another C2. The reason is that if you apply this one, for instance, this CO will go here, ligands will go here, and this ligand will go here. If you apply this, the same thing is also happening, right? So we have 2C2 axis perpendicular to C4 axis. So the answer is yes. Simply, the answer is yes. And do we have a sigma H plane? The answer is again yes. Why? Since if you apply a sigma H, so this is one of the sigma H, which is perpendicular to C4, and this CO will go here, this CO will go here, ligands will stay in the same positions. So we have sigma H. The answer is yes, and therefore our point group is D4H. So we made the first 2 steps, and then we have to find the reducible representation for CO, or the CO bond. So we have symmetry operations, E, C4, C2, C2 prime, C2 double prime, I, S4, sigma H, sigma V, and sigma D. So I want to write a CO, okay, and I want to draw the molecule here. So we are making, maybe I should show the bonds with blue, since we are making the representations to the CO bonds. Oops. I need a little bit more space. So this is our molecule, and I have to apply symmetry elements. So we have E element, which means that do nothing. So two bonds will stay in the same position. So we didn't do anything. Then apply C4. C4 is from here. It means that bonds will stay in the same positions. So we have two unchanged bonds. We have a C2. C2 is again from the top. We have C2 here, so that bonds will in the same position. However, if we apply C2 prime, and the C2 prime is from here, then this bond will go here and this bond will go here. Bond positions changed, so it is 0. And C2 double prime passes from here, so this is C2 double prime, and the same thing happens. Bond position change, in this case again 0 for C2 double prime. If you apply I operation, so if you apply the I operation, you will turn itself from here and you will apply a sigma H. If we apply the sigma H, bond positions will again change, so it is 0. Same thing happens if we apply the S4. Since S4 is also from here, you are applying sigma H after the C4. You will apply C4, nothing will change, but after the applying of sigma H, bond positions will change. Therefore, after the S4 operation, the number should be 0. We have sigma V. Oh, firstly we have sigma H. Sigma H is here, right? Then the bond positions will change, which means that it is 0. If we apply sigma V, which is this one, it includes the bonds, so that the answer is 2. And the same thing happens if we apply the sigma D, and the sigma D is from here, and if we apply the sigma D from here, similarly the same thing happens. Bonds stay in the same position, so it is 2. So if you want to find our reducible representation by using the irreducible ones, there is a method 1/16 times 1 times 1 times 2, right? 1 times 1 times 2, for instance, for A1G, to understand how many of A1G is there, and you have to apply it to the after the end. It is one way, but I will not use it since I know the answer. But if you want to do that, you can go on. And in many cases you may not enough time to do that, by the way, but I will say the answer. It is A2U plus A1G. If you add them up, 1 plus 1 is 2, 1 plus 1, 2, 1 plus 1, 2, 1 minus 1, 0, 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 1, 1, 2, 1 plus 1, 2. So this is the answer, our reducible representation, A1G plus A2U. So to understand whether it is infrared active, we are looking at the linear functions here. If it is Raman active, we are looking at the quadratic functions. So if you look at the A1G, it is only Raman active. If you look at the A2U, it is only infrared active. So we have two Raman active, one Raman active and one IR active modes. And if you have questions, you can ask in the comment section.